Okay, so next section here we're going to look at how to use an analytical approach, which means through the algebra, to determine what the end behavior is going to be. So we're going to find limits at positive and negative infinity using the growth rate stuff we just did on the last page, so dominant terms, who wins the race, that kind of thing. An end behavior model of functions. Okay. So we're going to look at each function and then we're going to rewrite them as being purely the dominant term. So we're going to throw everybody out that doesn't win the race because we don't care about them, and we're going to rewrite this. So my dominant terms, the dominant term in the numerator is going to be a 1, and the denominant term in the denominator is going to be the x. So as x goes to positive infinity, this guy is going to outpace 1 so much that there's something small being divided by something big, which means we're going to 0. Small over big means 0. Here we're looking at the limit of going to positive infinity, so let's throw out everybody that's not a dominant term. So that would be him, and that one, and that one, and that one. Okay, so sorry guys, one more time. So we would rewrite with our terms eliminated. So we're going to have 4x cubed over 2x cubed. So as x goes to positive infinity, this guy and this guy are going to grow at the same pace. So you'll have 4 infinities cubed over 2 infinities cubed. So these guys are going to reduce out no matter what they are, and we're going to be left with 4 over 2, which simplifies to simply a 2. Okay. This one, we're going to do the same thing. We're going to rewrite it with our dominant terms eliminated. So here we would have only this guy and only this guy. So we're going to rewrite it as x over the square root of x squared. And what's the square root of x squared? Just x. So as x goes to positive infinity, we're going to get 1 over itself, something over itself, which is just going to simplify to 1. We simplify that out, and we're left with 1. This one's a little bit trickier because we're looking at the same question, but in this instance, we're going to negative infinity. This is x approaching negative infinity, so do the same thing. Rewrite it with only the dominant terms. Just going to simplify to x over x. But this one's tricky because if you plug in negative infinity here into this guy, it's going to get squared and then square rooted. So negative infinity squared gives you positive infinity square rooted. So you're going to end up with a negative x from this guy, plugging in negative infinity, over positive infinity, which is not 1, but instead negative 1. So our note here would be to watch for squaring followed by square rooting, because that'll negate some of those negative symbols. Okay, so watch out for that. So let's look at some notation here. Let f be a function defined on the interval a to positive infinity. Then the limit of f of x equals infinity means that for every positive number, we're just using n here, there's a corresponding number n such that f of x is greater than m whenever x is greater than n. So we're going to go through this guy right here. So 3 to the x only leaves 3 to the x, and as x goes to positive infinity of this function, the whole thing is going to just go to infinity. E to the x, nothing to compare there, so this becomes e to the negative infinity, which we would rewrite as 1 over e to the positive infinity. So if I take this and multiply it by itself an infinite number of times, we're going to end up going to 0 because we have more weight down here in the denominator. Eliminating all but dominant terms here, that's actually going to do something. We'll be left with this guy and this guy. So we have e to the x over 4x to the 8th. And who's outpacing whom? Well, this guy is going to have more weight than this guy, which means that it's going to pull our answer up to infinity. So it's going to pull it up, and there won't be anything left that's having enough impact on the bottom to change that. So this guy's going to get really big over something else, like medium big, which ends up pulling us out to a positive infinity. Ends up pulling us just up and away. Now here, this guy's a little bit tricky, because we're looking at some absolute values and some natural logs. So if this one does not really click for you, that's okay. It's more of an extension question at this level, but we can come back to this after we've talked about logs if you'd like. So the natural log of positive infinity, if I'm going to positive infinity, that means that this number should be positive. Okay, so I can just say that I'm talking about the natural log of a positive number, because if I plug in a positive infinity into an absolute value, I get out a positive number. Over, there's nothing left in the denominator except for this guy when I eliminate dominant terms, which means this guy's the one winning the race. So who's bigger? You don't really need to know much about that. You just need to know who's going to win the race, this guy or this guy. So we can go back to our notes from the last session. Logs are going to fall over here on this end, and then polynomials here. So the guy in the denominator is winning the race. So we're ending up with our weight being big down here and small up here. And again, anytime you have a small divided by a big, you're going to end up going to 0. All right, so we're going to compute the limit of this function, and that'll help us to have a better understanding of how this works. So as x goes to positive infinity, we are going to square root of x squared plus x plus 1 minus x. Actually, I think I'm going to have you guys skip this one for now, because it's extension. If you want to go over this with me at lunch, we can.